Hello, everyone, and welcome to Climate Australia. I am your host, Lee Constable, and I'd like to start by acknowledging the traditional owners of the land on which I'm broadcasting to you from. So I'm on the land of the Gubbi Gubbi people, so I'd like to pay my respects to elders past and present and acknowledge the ongoing relationship that Aboriginal and Torres Strait Islander people across the over 250 different First Nations that make up Australia have with land, sea, and sky. Today, we have another of our episodes with the ARC Centre of Excellence for Climate Extremes. This episode is all about future extremes and how our climate change will affect the weather. So, of course, that is a very complex topic. We have dry extremes, we have wet extremes, and we have an interaction between weather and a fast changing climate. So, we've got three different researchers here to talk us through all of this. First, I'll introduce Todd Lane. So Professor Todd Lane is from the University of Melbourne. He's internationally recognised as an expert on tropical thunderstorms, atmospheric waves and turbulence, and his work at CLEX focuses on extreme rainfall using high-resolution cloud and weather prediction models. Welcome, Todd.
Thanks, Lee.
And joining Todd and myself is Michael Reeder. So Michael is a professor in the School of Earth, Atmosphere and Environment at Monash University. Prior to that, he held postdoc positions at the University of Munich, Germany, and the NASA Goddard Space Flight Center in USA. Michael's research is focused on the dynamics of weather. Welcome, Michael.
Oh, thanks, Lee.
And last but certainly not least, joining us is Claire Vincent. Dr. Claire Vincent from the University of Melbourne analyses and models tropical convection. Her research interests include tropical variability and precipitation, mesoscale meteorology, mesoscale modelling, and wind energy variability. So lots to talk about that there, Claire. Thank you for joining us as well.
Thanks, Lee.
Now that you're all gathered here, let's dive into the topic, which is about the interaction between weather and climate. We spend a lot of time in climate comms explaining to people that climate and weather are different while related, that climate's, the average of weather over decades, not just when it's windy today and not windy tomorrow. But now we also need to be able to explain to people the interaction between these things and how we can actually forecast in a changing climate and do things like that. So firstly, Michael, I will throw a question your way. What's the difference between weather and climate, more in depth than I explained there, and how do they actually interact?
Well, thanks, Lee. Climate is just the long-term average of various important properties of the atmosphere and ocean, as you said. But perhaps we can make this a bit more concrete. Let's think about rainfall, which is an important property of the atmosphere. And perhaps also to make it concrete, let's focus on Melbourne, which is where I am at the moment. I mean, for Melbourne, the long-term average of rainfall is 650 millimetres, which is 25.5 inches for those of you in North America. And of course, that doesn't mean that it rains 1.8 millimetres every day for 365 days, giving 650 millimetres a year. Of course not, that's not what we mean at all. I mean, in fact, in Melbourne, it rains for about 100 days per year. And when it rains, it rains in bursts, sometimes as long as a day, sometimes as short as 10 minutes. The point I'm making here is that the rain is produced by day-to-day variations in the state of the atmosphere. Whether these are weather systems, so fronts and cyclones and thunderstorms and sea breezes, etc. So to put that together, climate's a long-term average of rain and temperature, wind and clouds, whereas weather's that day-to-day change in the state of the atmosphere, the change in the rain and temperature, winds and clouds. In other words, what we experience every day. I know we're going to talk a bit more about the interaction between weather and climate later, but for the moment, I want to make the point that because of this inextricable link between weather and climate, a change in the climate really means a change in the weather. That's how we're going to experience climate change, as a change in the weather.
So yeah, I guess that's a thing that when people are asking questions of the media or whoever, when there's a big event a natural disaster or what have you, it's always, is this climate change? And it gets complicated because, like you said, those are interacting. Now, Todd, is extreme weather, and noting there are severe weather storms around where you are now, harder to predict than average weather?
That's a great question, Lee. And I think building on what Michael was saying earlier, these extreme weather systems could be a range of things. It could be a thunderstorm. It could be a sequence of rain events over a few days, which generate lots of rain. Or in the case of fire weather, it could be a combination of things. It could be a combination of long-term dry conditions, such as a drought, followed by some hot, dry days, followed by an intense cold front. And so that's a really bad fire weather day, so an extreme weather day. And now, one thing that all of these weather systems I've just spoken about, and tropical cyclones are another example, but one thing that they all have in common is their size. They're actually not very big. They're quite small in spatial scale, and they might be, in the case of a thunderstorm, 10 kilometres across, or in the case of an intense low pressure system like the one affecting Melbourne, where I am today, a few hundred kilometres across or 500 kilometres across. So they're relatively small. They're relatively small and relatively episodic. Now, when we think about how we predict our climate going forward, we use these global climate models. And the global climate models break the Earth up into these squares across the globe, and those squares are about 100 kilometres in size. And that's limited by the power of our computers. So if we're trying to predict the climate with a model that breaks the atmosphere up into 100-kilometre boxes, we actually can't do a very good job of predicting things that occur on scales that are smaller than those boxes. So thunderstorms are a great example that are just too small to be properly resolved in those climate models. Some of the intense cold fronts that we get on fire weather days are too small to be properly represented on those climate models. And so that's really one of the sources of uncertainty when we're thinking about extreme weather and extreme climate going forward, is that we have to make some inferences about how those are going to change, because we can't resolve them explicitly in our climate models.
Yeah, and so Todd touched on spatial differences and things like that, and that resolution. But Claire, I wanted to throw to you to talk about time, because when we're thinking about predicting, we want to know what's happening tomorrow, next week, the week after that in advance. How can we actually, in inverted commas, predict the weather in the future climate when we can't really predict current weather more than 10 days in advance?
Yeah, that's a really good question, Lee. And just building on what Todd and Michael were saying, it really comes down to the difference between the weather and the climate. So you're absolutely right. We have no idea if it's going to rain on the 29th of October, 2050. And that's absolutely not what we're trying to do. And instead, we try to understand not only what the average conditions are going to be in the future, but the whole distribution around that average. So two places can have the same average temperature, for example, but a very different variability around that average. And it's the peaks and troughs in the variability that brings us our extreme weather. So we don't try and predict, exactly when and where the extremes might happen. But if we know that distribution, then we can try to understand how often and how intense weather events might be without saying exactly when they'll happen.
Yeah, and of course this has implications, doesn't it? What sort of implications does this have for people in various sectors?
Well, the implications for this is that extreme weather brings hazards to areas such as coastal communities or aviation, for example. And so we need to try to understand the environments in which those extremes could occur, so that we can project the risk of the weather extremes in those sort of specific cases.
Yeah, it becomes a health and safety issue, and I'm sure an insurance issue or opportunity, depending who you are and what your sector is. Michael, a lot of us in Australia feel like we get heat extremes. We have. It's always been hot. We're really good at knowing all about what to do on a hot day or even in a heat wave. But what can we say about heat extremes in a warmer climate?
Well, perhaps we should. You've started off by saying we know all about heat extremes, but I think they're a lot more complicated than you might first imagine. There's sort of a simple part and a complicated part to it, and let's talk about how the heat extremes actually work, because that has something to. That is understanding that's sort of necessary for understanding how it works in a warmer climate. So let's talk about heat waves, and meteorologists have a particular definition of heat waves, although there's no sort of really standard definition. Mostly we think about heat waves as being 3 or more days of hot weather, where hot means upper 10% of days in that time of the year. And perhaps listeners in North America remember the record-smashing heat wave in late June of this year, and it affected the Northwest Pacific and Western Canada. And that heat wave is a good example of the underlying mechanisms. So prior to that heat wave, it rained over Asia, East Asia, near Japan. There was a little tropical low and it rained, and you think, well, that's no big deal. That's free. But that tropical low and that rainfall in the Eastern Asia set off a sequence of events which produced the heat wave over North America. What it did was it perturbed the jet stream. Now, the jet stream is a river of winds in the upper part of the atmosphere, maybe 10 kilometers high, something like that. And at that time of the year, it's directed from Asia to North America. And just the same way as when you throw a rock into a pond, those perturbations radiate away from Asia. But what's unlike the rock in the pond, these perturbations radiate along the jet stream. So it's directed from Asia to North America. And these perturbations grew in time and eventually grew so large that they produced a high in the upper part of the atmosphere over North America. You may say, well, what's that got to do with heat at the surface? Well, the thing is that when you produce these highs in the upper part of the atmosphere, they're associated with subsidence, sinking motion. And when air sinks, it's compressed because the pressure is lower near the surface. And when it's compressed, it warms. And this is a huge effect. When the air sinks a distance of 1 kilometer, it warms by 10 degrees.
Wow.
So it's a massive effect.
Yeah.
So I was going to say that the heat wave over North America was triggered by the precipitation in East Asia, and most of the heating came from air being compressed as it subsided. Now, even though that was an extreme heat wave, that sequence of events is pretty much how heat waves evolve. Certainly in Southern Australia, that's how they evolve. My point is that if we're going to talk about heat waves in a warmer climate, there's both a simple part and a hard part. The simple part is the climate's warming. So is that what climate warms will trigger this threshold for a heat wave more commonly. The hard part is, of course, heat waves depend on remote effects. Yeah. Effects over Asia affect North America. Effects over the Atlantic, things happening in the Atlantic affect heat waves over Southern Australia. And that's the hard part, getting this sort of regional, or getting these connections right. That's what's going to determine sort of the regional texture of heat waves.
Yeah, so one thing we're seeing from the IPCC report is that scientists are saying there will be more heat waves, that hot extremes will be greater, but we're really talking about predicting it really and linking these things together, aren't we here? We're trying to figure out how much of an effect and whether we can see the butterfly effect happening before it hits.
Yeah, so it's true. It's perfectly true. We're seeing more heat extremes, and we'll see more heat extremes. But the mechanics, the way in which these things work, depend on where's the convection. In the example I gave was over Asia, and that perturbed the jet stream. Where's the jet stream? How will that change in a warmer world? Will the convection change in a warmer world? For et cetera, et cetera. So there are a lot of links in the puzzle. And while we can say that we'll get more heat extremes, the details depend on changes in the winds and and the convection, and these things need to be handled correctly in our models to make accurate projections of what we should expect.
And it's the details that catch people out and can save lives or not, as the case may be.
It's the details we want. It's the detail. It's saying that we'll have more extremes in Australia, heat extremes. Well, that's fine.
Yeah.
But we really are interested in what were the heat extremes, how will they change for argument's sake, where I'm living in Melbourne, and that depends to part on the position of the jet stream.
And so one thing, oh, sorry, Michael. One thing that we've talked about on previous episodes with the Centre of Excellence has been about ENSO and El Nino and El Nina. And so perhaps to people, if you've listened or watched any previous episodes, that will be a more familiar thing that you can see a link between what happens far away and what happens closer to home in Australia. Claire, to bring you in on that, I wanted to ask how El Nino and La Nina affect the weather in Australia, and also touching on what Michael's just said.
Yes. Well, I think that the really fascinating thing here is that in our weather and climate systems, there's all sorts of things going on that have different sizes, and things of different sizes or spatial scales affect each other. And ENSO is a great example of this. It's really quite a large-scale thing that's being driven by the sea surface temperatures in the Pacific Ocean, where we've either got warmer sea surface temperatures in the Eastern Pacific and cooler sea surface temperatures to the north of Australia, or vice versa. And the location of those warm sea surface temperatures and cool sea surface temperatures drive where the large-scale upwards and downwards motion of air occurs in the equator, and thereby kind of drives the whole global circulation system, or modifies the global circulation. And then that drives a whole chain of downscale events, smaller scale events, including how likely it is to get certain weather extremes in Australia, but also in South America, North America, parts of Africa, and Asia. So in Australia, under La Nina conditions, we can see wet summertime conditions over much of the eastern part of the continent, and cooler maximum temperatures over much of the southern part of the continent, but conversely, warmer minimum temperatures in some regions. So that means less really scorching days, but potentially less relief at nighttime. And under El Nino conditions, we can see dry winter and spring conditions and warm spring and summer conditions, which can lead to extreme weather on quite a small scale, such as dangerous fire conditions or things like dust storms. So on a local scale, those variations in ENSO manifest as weather changes, which could be, for example, short duration, heavy rainfall events.
Yeah, so we're really talking about dry extremes and wet extremes for your different perspectives. Michael, did you have anything to add? Sorry, I think I cut you off over earlier.
No. The only thing I was going to add is since you're talking about La Nina, rather surprisingly, and this is sort of an example of this surprising connection. Surprisingly, we get more heat waves in Melbourne, not the rest of Australia, in Melbourne during La Nina. So, and it's because of the remote effect of convection on the formation of the heat wave in Melbourne. So, the only point I was going to make is it's sometimes surprising how these connections play out.
Yeah, absolutely. And I think the more we talk about these connections, the more that we can, if not answer people's questions who might be listening and watching, we can at least open their eyes to the number of complexities that you're working through in the research that you're doing. Todd, bringing you back in now, what do we know about and what don't we know about when it comes to changes in rainfall in Australia?
Well, the rainfall is probably much more uncertain, and future in rainfall is much more uncertain than some other quantities like temperature. Right? We've heard about heat extremes, and I think we're quite confident in aspects of changes of heat extremes and heat waves. But when it comes to rainfall, there's far less confidence. And there's a couple of reasons for this. And one is what I was talking about earlier about the climate models not being able to resolve those weather systems that actually produce the rainfall. So that creates a large amount of uncertainty in the future projections. But if you also think about what it takes for the atmosphere to rain, right? What are the ingredients that are necessary? There's a couple of key things, and one is moisture in the atmosphere. So all around us all the time. There's water vapor in invisible form in the atmosphere. And the interesting thing about climate change is that the amount of water vapor in the atmosphere will increase by 7% per degree of warming. So as the globe warms, the atmosphere can hold more moisture. And so immediately you think, oh, well, that should produce more rain and more rain everywhere. But that's just the thermodynamic component of this. And the other component is the dynamic component. So the wind and the weather systems that are actually extracting that water out of the atmosphere. And so it's those two things that work together that actually create the changes in our rain or create our rain systems. And so there's a lot of uncertainty about that change in circulation, the change in the weather patterns, the change in the frequency of those systems that will extract the water vapor out of the atmosphere, the change in the wind conditions that bring the moisture to certain locations, and the change in things like fronts or troughs or cyclones that will actually create those rainy systems. And so that's a big source of uncertainty. And so breaking it down, if we look at projections of climate change in Australia, for example, there are, if you average all the models together, the climate models together, they will produce a projection of changes of rainfall. And that varies regionally in Australia. In Southeast Australia, there's projected drying, and in northern parts of Australia, there's projected moistening, so it get rainier. But the key thing is that if you look at the agreement amongst the models, most of the models actually don't agree. So there's some of the models will say that it's going to get wetter in Southeast Australia, and some of the models will say it's going to get drier. And so that lack of agreement creates this uncertainty. So there's only a very small parts of Australia where we have confidence in the change in rainfall, and that area is southwest and Western Australia. So the southwestern tip of the continent is projected to dry, and all of the climate models agree with that. But if you look across the rest of Australia, there's very little agreement. And so I think we can say with confidence that we're actually not confident in the future projections of rainfall in Australia.
Yeah, and that is important to state, because if you don't state what we don't know, then you can't, as researchers, get attention around why you need to do your research, I suppose. We talk a lot about the certainty, and I think there's been a lot of push to talk about the certainty around these things. Is one of the reasons why there's disagreement between models just because of the fact that they were made when different assumptions held true more than they do now? Or, is it just with time and climate change, the models are having less and less agreement? Or I'm throwing that out to all of you.
Well, there are some things that the models agree on. And heat extremes is a good example. I think all of the models will say that the continental regions are going to heat up by a significant amount. But the amount that they're going to heat up depends on the model, changes with the model. But then once we go to some other things like rainfall, there is this disagreement. And there's each model is built slightly differently, using different assumptions, using different methods. Some may be slightly more accurate than others, but I think this lack of agreement represents some of the chaotic nature of how these systems work.
Yeah.
And all of the interactions. The rainfall in Australia does depend on the future state of El Nino. The rainfall in Australia does depend on the future state of the Indian Ocean. And it does depend on what's happening over the land, how much the land is drying out or moistening. And so if you add just a little bit of uncertainty to all of those things and bring them together, it actually creates a large amount of uncertainty in rainfall.
It gets amplified with the extra complexity. Well, I mean, everyone likes to get annoyed at the weather presenter when the weather's not right for the day. But I think if they understood the amount of complexity and the amount of amazing certainty on that time scale and across those spatial scales that we are able to get, they'd probably be more impressed than miffed if their daily forecast wasn't exactly right. Yeah, so obviously this is one of the things we're headed towards, that we're going to be seeing all of these impacts of climate change. Obviously COP26 is about to happen, and there are various political outcomes that will have, you know, big changes when it comes to, well, hopefully big positive changes when it comes to the assumptions that you can put into models. And modeling obviously is a big part of figuring out different potential impacts of different policy decisions. What do you think, you know, what are some of the things you wish that, even if they're known unknowns, that more people knew about who are working on various things to do with climate and our future? That's a big one, and I just sprung it on you, so sorry. No, I scared him.
I can jump in there.
Go for it, Claire.
Yeah, I can too. So I guess the first part of this interesting question is, right. So yeah, the first thing here is to really understand what we don't know in these questions, and so that is when we look at the large-scale changes in circulation and in the climate, then what weather types and phenomena such as fronts or thunderstorms are we missing that might influence the extremities of the weather?
Yeah.
And so then we have all our sort of future toolbox that we can apply to that, which in some cases is high resolution modeling. So as computing power gets more, then we can run models at higher and higher resolution and start to really resolve some of those things. But we also need to understand the statistics of the uncertainty of those events. So, and then I guess the other part of it is the physical processes. So we need to understand both how many fronts might occur in the future, but also what kind of hazards are going to be associated with those fronts under a changed climate.
Yeah, absolutely, because it's not just about mitigation, it's about adaptation, isn't it? And it's about preparing for things. It's about giving everyone the best chance of a safe and healthy life. So all these things definitely matter. Claire, to finish this off before we go to a few questions, I just wanted to ask about predicting the weather and severe weather. What might change in the future on predicting severe weather?
In terms of forecasting the short-term forecast.
Sorry, I should say forecasting, because we don't actually need to say predicting, right? Is that a misnomer for what happens?
I think that's okay. Well, yeah, that's a good question. I mean, I guess as the climate changes, some of our kind of conceptual models or ways of forecasting might, you know, if we're in a sort of non-steady state system, things might sort of need adjusting as we move forward. But probably on that kind of short time scale, I don't know that I'm not really sure that the predictability in that sort of, you know, few days outlook is going to be terribly different. You know, given what we can predict on those timescales.
Yeah, so it's more the long-term adaptation measures that might, you know, be an implication from the changing models, and might be a positive outcome as an opportunity to have longer-term ways of preparing, of thinking about severe weather, than short-term is going to be potentially similar to how we predict it now.
I think if I can jump in, I think one of the big differences in how we'll see future predictions of severe weather is actually around uncertainty. Rather than saying it's going to rain tomorrow or there'll be a thunderstorm tomorrow, it'll break down into a much more probabilistic message. And I think this is also important for estimating and communicating climate risk going forward, is introducing this idea of uncertainty. And it's something that we don't deal with very well as people, as a community, and it's something that's often not communicated well. And everyone's decisions are different. So if I said to you, Lee, it's going to rain, there's a 50% chance of rain tomorrow, you may decide to take an umbrella. But if I said the same thing to Claire, she may not decide to take an umbrella, right? So we all make decisions based on
Yeah.
probabilistic information in different ways.
And then there's someone else who might see that it's rained in the morning and be like, there was only meant to be 50% rain, so I should be fine for the afternoon.
Yeah,
which is a complete other interpretation of what you said.
Absolutely. And so I think both for short-term forecasting, this idea of uncertainty is going to come into play, and also for policy implications and estimation of climate risk going forward. I think the key thing is around uncertainty, especially about some of these things that we don't really know. Right? Changes in rainfall, changes in storms, they're much more uncertain.
And honestly, given the pandemic and people's levels of uncertainty and probability and risk, I like to think that will help when it comes to figuring out the best way to communicate these things, but we'll have to see. And Claire and Todd, as you mentioned, having good understanding of how to communicate statistics and probability and really getting those messages through is definitely something that I'll be thinking about as a climate communicator going forward. So thank you both for adding those. So now we're just going to go to a bit of a credit scene, and then we'll be back for a Q&A. So thank you all for joining me on another awesome episode with the Centre of Excellence for Climate Extremes, and we'll be back after this. All right, we're already back. On our end, it didn't look like anything changed, but on your end, you've seen some credits. I've got a few questions here. Firstly, I've got one for you, Todd. If the atmosphere is warmer and we're seeing more extremes on the ground, is this also true in the air? Will we see changes in turbulence when we fly?
That's a good question. So there has actually been a fair bit of work recently on looking at how the aviation industry are going to be affected by climate change, and there's a number of ways that they can be affected, and I'll try not to go on for too long about this because I probably could. Through changes in the wind systems, like the jet stream, if the jet stream shifts or moves or gets stronger, that can move it into existing flight paths and make the atmosphere more turbulent. And so there's quite a lot of work that is showing that those flight routes between North America and Europe will likely become more turbulent as we get changes in our climate going forward in the next century. But the other aspect is around turbulence around thunderstorms. So thunderstorms generate turbulence through a whole range of processes. And aircraft try and avoid them by flying around thunderstorms, but oftentimes this turbulence can occur in the 10 to 20 or 30 or 40 kilometres around those storms where aircraft will still fly. Now, if our storms become more intense, and there is certainly an indication that with the enhanced water vapour in the atmosphere, those storms could become more intense, then it's possible that the turbulence generated by those storms becomes more intense as well. So that may mean that aircraft need to divert a little bit further around those storms in the future. It also may mean that if we get areas that become more stormy, they're going to be more difficult to fly through and may need to be diverted around.
Yeah, an important thing to think about. Not that many of us have been flying recently, but I'm sure that will increase again. Michael, heat, wind, droughts, can lead to extreme events. And of course, fires, we mentioned briefly. There's a general idea that fires in Australia will get worse as climate changes, but is that something we can say with so many different contributing factors? And is there anything we can say about how fires might change?
I think this is a very tricky topic. So I think the first thing to say is that the big fires in Australia and most places are very firmly connected to drought. The last, Black Summer, Ash Wednesday, the fires in Canberra in 2003, Black Saturday, they all came at the end of prolonged droughts. The prolonged drought dries out the fuels, not just the fine fuels, but the heavy fuels. So you've turned vegetation into fuel. That's the first thing. We also know that all our big fires are connected to, all our big fire days are connected to cold fronts. Black Saturday, huge cold front. You know, the front came through, changed the temperature by 20 degrees in a few minutes. Ash Wednesday, the same. So they are big ingredients for these big fires. Now it's perfectly true. So first of all, the change in the fire problem amounts to how a drought's going to change. Really, that's what I think it amounts to.
Yeah.
And that's a bit tricky. So it seems that there is signal in the models about changes in droughts in the southwestern part of the continent. The rest of the country, it's a bit harder to say. It's certain that the fire season has lengthened with the warmer conditions and the slightly dry conditions, but big fires, I think we've still got some work to do on that one.
Yeah, and I know that previously we've done an episode with Clex on drought and talking about whether drought is kind of the norm that Australia turns back to as opposed to a blip, and figuring that all out is
so fires difficult. Are kind of a knock-on effect of drought, and as you probably talked about with colleagues in a previous episode, it's a tricky problem. How drought's going to change.
Yeah. Each of you have a lot of questions that you're researching. I wanted to give you each an opportunity to let me know if there was one of your research questions or an unknown that you wish you had the answer to and that would make your research a whole lot easier. What would it be? I'll start with you, Todd.
I'd actually quite like to know how thunderstorms are going to change in the future. And as we talked about earlier, there's so many ingredients that come together to create thunderstorms and are going to affect how they change in the future. It's a question people often ask me, and when we have storms like we did in Melbourne just last night, people say, wow, is this due to climate change? And we have so much uncertainty around the answers around those that we can't really say yet. And I'd like to really progress this, and this is part of our research going forward, both in our centre and probably beyond our centre as well, that how a thunderstorm is going to change. And to do that, we need certainly much more fundamental research, even into how thunderstorms form, but also much better tools to study them. And those tools are really high-resolution climate models, much higher in resolution, able to resolve much smaller scale features than we currently have available to us. So it's a massive computational problem, which is pretty interesting and exciting to study, but I wish we had the answer now.
Yeah, if you had Jeannie, that'd be, I'm sure, one of your wishes. How about you, Claire? What would your question that you'd love to know the answer to ASAP be?
I would like to know in a very detailed, fine-grained way what coastal weather is going to look like in the future. So around 40% of the world's population lives in the coastal fringe. And it doesn't always behave how the rest of the continents behave. It's sort of got its own weather and climate. And it's also very small scale that, the whole coastline in a climate model is just represented by one grid box. And yet there's so many things going on there with sea breezes and the often mountains near coasts and severe weather, and coupled with like risk of inundation. I just think it's a really important region to understand in the future.
Yeah, and just before we went live, I think it was Todd who asked about hail where I am, because I'm just north of Brisbane, but because I'm on a little peninsula, we often just miss it. But, only a few blocks down there gets it. So you're right, it's so much more complex than we can really illustrate in a big coastal band. How about you, Michael? What's your top question you want the answer to?
Well, I think the question that I'm interested in is how extremes then feed back on the weather and climate, not just one way, but the back reaction. And I'll give you an example. I'm interested in the dynamics of the monsoon. How do wet seasons, how do they work, particularly the wet season in Australia? And if you think about the wet season in Australia, when there's extreme convection, extreme rainfall, right, in northern Australia, then the monsoon trough, that's the low pressure system in which the thunderstorms are developing in the wet season, jumps. And it jumps very dramatically southward. It might jump 500 kilometers southward. So there's a very clear connection between not just regular garden variety wet season rainfall in the Australian tropics, but extreme rainfall in the tropics then has some back reaction on the local circulation. I bet this is true for lots of extremes, and well, certainly true for heat waves as well, but there is a back reaction. But this is one clear example of it, which I don't know what the answer is. But I think that investigating this back reaction of extremes on the larger scale circulation perhaps is something that I personally would like to know more about.
Yeah, well, it sounds like you've all got a lot of questions that perhaps keep you up at night, but also make you jump out of bed in the morning to go back to work and keep asking and answering them. We've got a few more minutes left, and I've got a couple more curly questions here. For Todd, this is a sci-fi question. It sounds like sci-fi. Well, it sounds like sci-fi. Might be less fi, more sci. But on a number of occasions, Alvin has heard climate researchers talk about gravity waves in the atmosphere coming from large thunderstorms. What is an atmospheric gravity wave, and what kind of impacts do these waves have? And this is the first time I'm hearing about it reading this question, so I'd love to know.
Oh, great.
Great.
So, no, I'm happy to answer this question. So we have to be very careful with our language here because physicists also talk about gravity waves, which are actually gravitational waves, ripples in gravity. But what we're talking about here, atmospheric gravity waves, are also often called buoyancy waves or internal waves, and they're ripples or oscillations in our atmosphere that occur due to the atmosphere getting a jiggle, right? And the good analogy is if you throw a stone into a pond and you get these ripples that spread out, it's the pond that is restoring back to its original location. You displace it by throwing the stone in, it gets perturbed, and then it creates this oscillation. Now that happens in the atmosphere, and these gravity waves are basically everywhere because any weather system that jiggles the atmosphere a little bit will create these waves, and they survive because the atmosphere is what's called stably stratified, which means that if you move a piece of the atmosphere around, it wants to go back to its original location. And so thunderstorms generate these waves, mountains generate these waves. You'll often see clouds in wave-like patterns near mountains, and these are atmospheric gravity waves. Other storms generate them too. So they're basically everywhere, and they're very similar to waves in the ocean as well because they'll break, and when they break, they mix things up, and they mix up constituents. They can help transport chemical constituents from the upper part of the atmosphere to the lower part of the atmosphere. They create turbulence. They're a hazard to aircraft as well. So they're actually a pretty important part of the climate system.
Well, thank you for opening my eyes to that because I had no idea. The more you learn, the more you don't know when it comes to climate, it seems. Thank you all so much for joining me and for demystifying some parts of climate and also telling me more about the known unknowns, so I'm aware of them as well. Thank you, Todd. Thank you, Claire. And thank you, Michael.
Thank you, Lee.
Thanks,
Thank
Lee.
you.
All right. See you next time, everyone.